Okay, so first of all, thank you, especially thanks for to the organizers for organizing this meeting and these particular circumstances. So I will be today here discussing the characterization of even-dimensional Kerr-de Sitter and its limited spacetimes, which is a work in collaboration with my advisor Mark Mars. So let me start with a brief introduction of the ideas I will discuss today. As you know, Kerr-de Sitter are metrics which represent rotating black holes in a universe with positive cosmological constant. So for a fixed value of the cosmological constant and in 4 dimensions, Kerr-de Sitter is a two-parametric family of metrics depending on mass and rotation parameters. In higher dimensions, more rotation parameters are added. And in the positive cosmological constant setting, the cauchy problem happens to be well posed at conformal infinity. So what we have done is to use cauchy data at conformal infinity to characterize this Kerr-de Sitter family in all even dimensions, as well as its limited spacetimes. So now I'm going to discuss the asymptotic cauchy problem in general relativity and related results in 4 dimensions first, and then I will generalize it to more dimensions. So let M tilde G tilde be a Lorentzian manifold in 4 dimensions, which is Einstein, and assume that M tilde G tilde admits a smooth conformal extension, which is a conformal scaling of the metric, which is regular on a bigger manifold M tilde plus one hypersurface, which I will call scry. This hypersurface is the zero level sets of the conformal factor where the gradient of the conformal factor doesn't vanish. And this represents infinity in a conformal sense. So for the positive cosmological constant case, this hypersurface scry is known to be a space-like hypersurface. And then we have this classical theorem by Helmut Friedrich from the 80s that asserts that for every space-like 3 manifold, sigma, gamma, and D are symmetric to covariant TT tensor. These are the data of the cauchy problem. D is a TT tensor, which means that it is traceless and without divergence. Then there exists a unique maximal globally hyperbolic solution of Einstein equations with lambda positive, admitting a smooth conformal extension in such a way that in the conformally compactified spacetime, scry corresponds with the manifold of the data, and D determines the so-called electric part of the rescaled Weil tensor. And in this cauchy problem, this data happen to be equivalent under conformal scalings of the manifold. This is if we scale the metric by a squared conformal factor and the TT tensor by the inverse of this conformal factor, then these two sets of data correspond to the same spacetime. Here, a very schematic picture of the asymptotic cauchy problem. We post data on scry and we generate a piece of conformally compactified spacetime. When we undo this conformal transformation, we obtain this G tilde metric, which is the one which satisfies Einstein equations. And this metric extends to infinity in one direction. So concerning spacetimes with symmetries, we have this theorem by Patz from the 2016 that he has proven that 4-dimensional spacetimes characterized by data, sigma, gamma, D, then the corresponding spacetime has a Killing vector field if and only if this equation, which is called the Killing initial data equation, is satisfied, where this L stands for the Lie derivative with respect to psi, being psi a conformal Killing vector field of sigma gamma. So with this, I can now define the Kerr-de Sitter-like class with conformally flat scry. I will denote this class by a strongly Kerr-de Sitter class in this talk. Let me remark that when I say class, I'm going to refer to a collection of several families of the spacetimes. So the strongly Kerr-de Sitter-like class contains several families, among which the Kerr-de Sitter family is. So the Kerr-de Sitter-like class of spacetimes are solutions of lambda positive Einstein equations. of lambda positive vacuum Einstein equations, admitting a smooth conformally flat scribe, as well as a Killing vector field, and their so-called maximum tensor vanishes. At the level of the data, this class of spacetimes is defined by data sigma gamma d, where sigma gamma is obviously conformally flat, and this d psi is a TT tensor which has this form, where psi is a conformal Killing vector field of this manifold, and it is remarkably simple among all TT tensor which one could obtain in a conformally flat manifold. So d psi satisfies the Kidd equation for psi, and for every conformal transformation of sigma gamma, then we have the following equivalence of data, which arises from the structure of the TT tensor as well as the conformal gauge freedom of the data. And this equivalence is translated into the fact that the families within the Kerr-de Sitter-like class are characterized only by the conformal classes of conformal vector fields. This is the conformal vector fields modulo conformal transformations. Moreover, this TT tensor, d psi, generalizes to a TT tensor in arbitrary dimensions by simply changing few numbers, this exponent here and this number here, from 3 to arbitrary n. And this TT tensor satisfies this equation, which recovers the Kidd equation for n equal to 3. So the question now is natural. Can we extend the strongly Kerr-de Sitter-like class to arbitrary n+1 dimensions, being, for the rest of the talk, n+1 the dimension of the spacetime, so n is going to be the dimension of a scribe. If we can extend this definition, what are the spacetime corresponding to this extension? And before giving this extension to more dimensions, I will have to discuss briefly these topics here, the data at conformally flat space like scribe for more dimensions, the generalization of the Kerr-de Sitter metrics. We must verify that the Kidd equation is equivalent to symmetries also in more dimensions, and the Kidd equation is going to be this one for dimensions bigger than 4. And we have also to study the conformal classes of conformal vector fields in arbitrary dimensions. So concerning the Cauchy problem in higher dimensions, we have this result by Anderson that extends the existence and uniqueness result to arbitrary even n+1 dimensions. What is even is n+1, so n is going to be odd. In this case, the data are also a manifold, a Riemannian manifold, and a TT tensor. And the Riemannian manifold corresponds to the geometry of a scribe, and V is the nth order coefficient of a certain formal series expansion called the Pfefferman-Graham expansion. It's a formal series expansion in omega of the conformal metric. And this Cauchy problem, this also keeps the conformal scaling freedom, but now when we scale the metric by a conformal square factor, the TT tensor must be scaled by a power which depends on the dimension. Obviously, setting n equal to 3, we obtain the usual result. And the thing is that when one tries to calculate this nth order coefficient of the formal series expansion, this is not a direct calculation, it's more complicated. So we asked ourselves whether this coincides with the electric part of the rescaled Weil tensor, and we found that for Cauchy data at the space like scribe, when the manifold sigma gamma is conformally flat, then D agrees with the electric part of the rescaled Weil tensor, being the rescaled Weil tensor now rescaled by a power of omega, which also depends on the dimension. And let me stress here that this result is true for the conformally flat setting, but it's not true in general, because this tensor here is in general divergent. In addition, we have also proven that in arbitrary dimensions, the Kidd equation is a necessary condition for having symmetries. And in the case of analytic metrics, it is also sufficient. And analytic metrics correspond to analytic data. So now let me give you a classification of conformal classes of conformal vector fields. This, we have done it in arbitrary dimensions for odd and even parity, but I'm going to discuss just the odd parity case because it's the one we are discussing in more depth. So let psi be a conformal Killing vector field of a conformally flat Riemannian manifold with n odd. Then there exists a conformal representation of the manifold which is locally isometric to the Euclidean space. So it's a locally conformally flat representation into which psi admits a decomposition of this form where these mu I are real positive parameters, and these adding terms are vector fields which are pairwise commuting and orthogonal, and each of the eta I are generators of rotations, and tilde psi depends on one real parameter, sigma, in such a way that when sigma is positive, then tilde psi is the generator of a rotation. If it's 0, it's the generator of a translation, and if it's negative, it's the generator of an homothéty. With this decomposition, these parameters determine the conformal class of psi. But this relation is not univocal because one can always permute these parameters. So we have set a certain order. These mu parameters are ordered in decreasing order from the biggest to the lowest. And when sigma is positive, it's the biggest of all them. When sigma is negative, we keep the order in the mu's, and sigma is the only negative or zero parameter. With this order, now the conformal classes can be represented in a diagram mu sigma squared, and we have calculated the quotient topology, and it happens to be non-Hausdorff, which has interesting consequences in our analysis. So the generalization of the Kerr-de Sitter metrics to more dimensions was given by Gibbons and collaborators in 2005, and this generalization adds more rotation parameters. And obviously, for the case n equal to 3, it recovers the usual Kerr-de Sitter metrics. So we have taken this generalization of Kerr-de Sitter metrics, and we have shown that they always admit a smooth conformally flat scri. And we have also shown that the electric part of the rescaled by tensor at scri has this form, which is the one we expected to obtain, being psi a conformal Killing vector field of scri, whose conformal class lies in the region of negative sigmas. Now, with these results, it makes sense to extend the definition of the strongly Kerr-de Sitter-like class to arbitrary even dimension by data which are a conformally flat scri and a TT tensor of the form of this form, where psi is any conformal Killing vector field of scri. Likewise, in the four-dimensional case, we still have the same equivalence of data for every conformal transformation, which is again translated into the fact that only the conformal class of psi matters to characterize families within the Kerr-de Sitter-like class. So to understand a little bit the structure behind this class, let me start with the n equal to 3 case. Here I have depicted a diagram of the parameters representing the conformal classes. This shadow region must be removed due to the order we have given to the parameters to be this relation to be univocal. And very briefly, let me discuss the families in this class. In this section, the negative sigmas, we have the Kerr-de Sitter family. In this sigma positive region, we have the weak rotated Kerr-de Sitter. And in this vertical line, we have a particular limit of Kerr-de Sitter when the rotation parameter goes to infinity. And in the horizontal line, we have the so-called the generalized Kotter spacetimes, given by these metrics, where gamma is a two-dimensional metric of constant curvature given by the sign of sigma. So, for instance, we have here Schwarzschild-de Sitter. Here we have at this point a spacetime which is similar to Schwarzschild-de Sitter, but with flat two-dimensional sections. And in this part of the region, we have hyperbolic two-dimensional sections. So it happens that in the quotient topology, sequences of R minus assuming limit at L2, they also assume limit at L1, and in a similar way, sequences assuming limit at L1 from R plus also assume limit at L2. This, which happens at the level of the data, since the Cauchy problem is well posed, it also induces limits at the level of a spacetime. So the Kerr-de Sitter spacetimes have limits in the spacetimes corresponding to this line, but also in the spacetime corresponding to this line. And in a similar way, the weak rotated Kerr-de Sitter has limit within the spacetime corresponding to this line, but also with the spacetime corresponding to this line. So this idea generalizes to arbitrary dimensions, even dimensions, of course, which is the case where we have guaranteed the well-posedness of the Cauchy problem. But the more dimensions we add, there are more parameters, and then there are more limits which we were able to calculate. For instance, the limits of Kerr-de Sitter when the rotation parameters go to infinity, because in more dimensions there are more rotation parameters, so you can define several limits for different number of rotation parameters going to infinity. And we were able also to construct all the spacetime which recover all the data in the class. This took us to generalize the weak rotated Kerr-de Sitter spacetimes, which are those that corresponds to in the conformal classes of vector fields correspond to the regions of positive sigma. Here I have depicted the n equal to 5 case to see that this structure is a little bit more involved than in the n equal to 3 case. We have two mu parameters, and this surface of sigma equal to 0, one could accede from below, but one could also accede from this mu equal to 0 surface. And let me stress again that this structure, which is very clear at the level of the data, it is not at the level of spacetime directly. So summarizing, we have proven that in all even dimensions, the initial data at conformally flat space like Scri corresponds to the conformal structure of Scri and the electric part of the rescaled Weil tensor. We have extended the Kidd equations to arbitrary dimension for the analytic case, but we believe that this is going to be true in the non-analytic case as well. And we have defined the strongly Kerr-de Sitter-like class in all even dimensions by data at the Scri. And we were able to construct all these spacetimes that realize the Kerr-de Sitter-like class data, finding new limits and new spacetimes. So I think I will stop here.